Hi, so we're going to be answering question 29 from the 2024 CSSA Math Advanced trial paper. So for question 29, we have an astronomer is attempting to predict the height of a satellite above the ground as it orbits around the Earth. Where you use precise measurements, the height of the satellite can be modeled with the function h in terms of t is equal to 6 sine pi on 6 t minus 15 plus 8, where h of t is the height of the satellite in thousands of kilometers at time t hours since midnight on any day of the year. The first part of this question wants us to find the minimum and the maximum heights reached by the satellite. And whenever we have trig functions like this, whenever they ask for the maximum or the minimum heights, that has to do with the amplitude of the function. So we can find the amplitude of the function by looking at which number is sitting outside of our function. So this number here, 6, is going to be our amplitude. We can take this in reference with our regular sine graph. So our regular sine graph has a maximum value of 1 and a minimum value of -1. It also has an amplitude of 1. The graph that we have here has been dilated, so it now has a amplitude of 6. So we can imagine this as being stretched out by 6. So therefore, when we now take in our values of our maximum and minimum, they're now going to be times by a factor of 6. We also need to take into consideration the fact that this graph has been shifted up 8 units. So now if I want to find my minimum value, I can take my usual minimum value of a regular sine graph of -1, times that by my new amplitude of 6, but make sure I also add up my 8 units. That's going to take into fact that it's been shifted 8 units upwards. So here I have -1 times 6 plus 8, which is going to give me 2. Same thing for my maximum value. I can now do my usual maximum value of my regular sine graph of 1, timesing this by my new amplitude of 6, and then plussing this by 8 units up. So I have 1 times 6 plus 8, which is going to give me 14. Now I can't leave my answer like this because at the moment I have my answer written as my minimum value is going to equal to 2 kilometers and my maximum value is equaling to 14 kilometers. This is going to be incorrect just because this is measured in thousands of kilometers. So therefore my minimum value is actually going to be 2,000 and my maximum value is going to be 14,000. Okay, now that we've found the maximum and the minimum values, we can then move on to find the sketch the graph of h of t between 0 and 24. So what you need to do is draw your vertical and your horizontal axes, labeling your horizontal axis as t and your vertical axis as h in terms of t. Now I want to include the entire domain of t, so my last values here is going to be 24, and I can then move up my graph in increments of 2. Likewise with my vertical axes, I want my maximum value here that we just figured out to be 14,000. So I want to leave myself enough room to do that. I don't have enough room to go up by increments of 1, so I'm going to move up by increments of 2 again. Okay, the next thing I want to find out is how many complete rotations of my graph I can do within my given domain. And the way that I can find that out is by working out what my period is going to be. So I have my period function as being period is equal to 2 pi on b, and this is the same formula that you would use for any cosine or sine function. Now we find out what our b value is going to be by looking back at our equation. So our b value is a number that sits outside of those brackets. So b here is going to be pi on 6. So since our period equation is given by period is equal to 2 pi divided by b, we can rewrite this as being 2 pi divided by pi on 6. So I can cancel some terms out. I'm going to change this into a multiplication equation by going 2 pi times its reciprocal of 6 on pi. And I can then cancel out these pi's and I'm left with 2 times 6, which is going to give me 12. So what this means is that every 12 values of t, my function is then going to restart. So at this point here and at this point here. Okay, the only other translation that we need to take into account is the fact that it's been translated 15 units to the right. This is going to change the general shape of the curve just because it's going to change where it starts on the x or the y axis. So for example, if I have a look back at my regular sine function, let's say I want to shift it this many units to the left. So I'm starting at my pink dot there. If I then draw that same function from there, I'm going to be having this, and it's going to look a little bit different to what my regular sine curve is going to look like. So one of the best ways to figure this out is actually find out where this point is, and that point there is going to be your y-intercept. So we can find our y-intercept by making t in our equation equal to 0. So we have y is going to equal to 6 outside of sine pi on 6 t minus 15 plus 8. When you plug that into your calculator, you get y is going to equal to 2. So therefore my y-intercept is going to be here at 2. So therefore that's where my sine curve starts. You can then draw in your sine curve, making sure that it does one full rotation by the time that it gets to every t is equal to 12. Perfect. I need to draw two end values because I've been given an inclusive domain, so I can have a value of 0 and I can have a value of 24, and it's because it's a domain, I need to make sure that it's two ended points there. Okay, so now that we've sketched the function, we can then move on to part C. So for part C, we have the satellite is out of range if it's higher than 11,000 kilometers above the ground. So we need to use algebraic techniques to find how many hours in the day the satellite is out of range. So if we refer back to the graph that we just drew, we're trying to find out for how long this function here is above this line of when the height is 11,000 kilometers. Like that. So therefore, we're trying to find the total length of these highlighted parts here in terms of t, because we're solving for t here. Okay, so if we're going to be solving this algebraically, we want to let this function equal to 11. So 11 is equal to 6 sine pi on 6 t minus 15 plus 8. And we're trying to solve for t. Okay, minusing both sides by 8, I get 3 is equal to 6 sine pi on 6 t minus 15. I then want to get rid of my coefficient at the front of my fraction, so I'm going to divide both sides by 6. So I get 0.5 is equal to sine pi on 6 t minus 15. Okay, I'm still solving for t here, and the only way that I can get rid of my sine is by taking sine inverse to the other side. So I'm going to let this entire thing here now equal to theta. And my usual domain there was between 0 is going to equal to, t is going to be between 0 and 24. But now because I have my t being pi on 6 times t minus 15, I also need to reflect that change in my domain. So therefore my domain is going to change. So now I have a domain of my new variable theta, which is going to be found by substituting in my previous domain points. So what I mean by that is go pi on 6 times 0 minus 15 is going to be my starting point. And then pi on 6 times 24 minus 15 is going to be my ending point of my domain. So negative 15 times pi on 6, you're going to get negative 2.5 pi. Pi on 6 times 24 minus 15, you get 1.5 pi. So therefore that's quite different from what I originally had. So I'm going to be using this new domain to see how many values of t I can get. So I know, looking back at my equation here, I know that my sine is going to be positive at 0.5, and my sine is positive in the quadrants 1 and quadrants 2. So sine 0.5 is going to give me pi on 6, or 30 degrees. So I have pi on 6, this entire thing here, or my theta, t minus 15, is equal to pi on 6. I can also take the pi minus pi on 6, so my 180 minus pi on 6, or my 180 minus 30, which is equal to 150, or 5 pi on 6. These two fit in my domain. However, I can't add another revolution to that because I'll then be going outside of my domain of 1.5 pi, but I can move the other way. So my ending domain of my new domain is negative 2.5 pi. So I want to see if I can go the other way and see if I can get some more values of t. So if I do pi on 6 minus 2 pi and 5 pi on 6 minus 2 pi, I end up getting negative 7 pi on 6 and negative 11 pi on 6, both of which are in my domain. But I can't take another revolution back from that, and I can't take another revolution forward from that. So those 4 values are the only 4 values I can have for now. I then want to keep solving for t, so I really want to isolate t here. So I can divide both sides by its coefficient of pi on 6. If I divide both sides by that coefficient, it's going to get rid of my pi on 6 and all my numbers here. So I'm going to get t minus 15 is going to equal to 1, 5, negative 7, and negative 11. Then all I need to do here to get t by itself is add that 15 back on. And I got t is going to equal to 16, 20, 8, and 4. Okay, so in reference back to my graph now, I can see that my values of when we were these endpoints here are going to be 20, 16, 8, and 4. But I'm trying to find the length. So I can find this length by going 8 minus 4, and I can find this length by going 20 minus 16. So therefore I have 20 minus 16, which is equal to 4, and 8 minus 4, which is also equal to 4. So therefore the total amount of times per day, because there's 24 hours in a day, is going to equal to 4 plus 4, which is going to be 8 hours. It's out of range per day. And that's how we figure out question 29 from the CSSA 2024 trial paper.